Hello and welcome to the Scientific Adventures of Beardman. Today we're going to take a little adventure and do some time traveling. Well, first let's just remember from the last video we learned that light, the last two videos, that light is crucial for understanding the universe. And we learned that one of the things we can do with light is analyze the spectra of it, what wavelengths are coming through. And that can tell us about the types of elements that released that light. Okay? There's many other things we can understand about light, but that's the one we're going to focus on. The second thing we have to understand about light is that it takes time to travel. Okay? If light leaves somebody like you, or the computer screen, me, if it leaves me heading towards you, it takes time to get from the screen to your face, okay, to your eye. And then, of course, there's also some time for your brain to process it. But we're just going to talk about the time for the light to get from the screen to your eye. So when you see me doing something like, boo, okay, then you actually didn't see me doing that until, I don't know, at least a nanosecond after I did it. Okay? I guess it depends how close to the screen you are. But assuming you're about a meter away, then about a nanosecond later, you would have seen me going, boo, okay? And so you could, if you're a student in class, you could be thinking, hey, I can get away with anything for a nanosecond. And then the teacher will catch me. Well, that's true, but of course, who cares about a nanosecond? We don't care about that. I'm going to live free for a nanosecond. Okay, ridiculous, right? Okay, but when we start getting to the distances in space, it starts becoming more and more important. Okay, when we look at the sun, you may have heard, it's a Trivial Pursuit question from the good old days, that it takes 8 minutes for light to get from the sun to Earth. Meaning that there's a solar flare on the sun. The light leaves as that solar flare is happening. The light from that solar flare leaves, and 8 minutes later, our telescopes receive that light, and we see the solar flare. Okay, so that solar flare had happened 8 minutes prior. Well, the nearest star to us, Proxima Centauri, is 4.22 light years away. That means that it took light 4.22 years to get to us from Proxima Centauri, which tells us what Proxima Centauri looked like 4.22 years ago. Okay? If Proxima Centauri were to supernova or do anything weird, stop glowing, we wouldn't know about it for another 4.22 years. And we'd see it and we'd go, oh, Proxima Centauri just did this. It'd be all over the headlines. And of course, it really happened 4.22 years ago. Well, okay, who really cares about 4.22 years? It's only 4 years, and we're, we see it when it gets to us, and that's what really matters to us, right, is when it gets here. The nearest galaxy to us, nearest major galaxy, is Andromeda. It's a spiral galaxy, kind of like our own, and it takes light 2.5 million years to get to us from Andromeda. So when we look at Andromeda, we're seeing what that galaxy looked like 2.5 million years ago. Okay? That's a long time. And you might figure galaxies would change in that time, so Andromeda may look different. Well, 2 million years is actually very small on the scale of evolution of a galaxy or change within a galaxy. Now, as you go farther and farther away, it gets older and older. Or if we could teleport instantly to far enough away, we could look back with a really powerful telescope and see dinosaurs roaming around on Earth. Okay? So if we keep looking farther and farther back, if there was some beginning to time, in theory, we could still see it. That's an interesting thought. So far enough away, we could see the beginning of time, or the beginning of the universe. What is it? I don't know. Well, first of all, one major assumption that we make when we're thinking this way about the universe is we make the assumption that the universe is the same everywhere. What? Clearly the universe isn't the same. I mean, I can go outside and I can step on the ground, or I could go 30 minutes down to the beach and step in the ocean. It's clearly different in different places. I go, 100 kilometers up and essentially there's nothing. And here there's rocks and everything. How can you say it's the same everywhere? Well, why am I talking to myself is the other question. When we say the same everywhere, we mean it follows the same rules. Okay, that the universal gravitational constant is the same everywhere. Now, we can't really go anywhere except for the Earth and the Moon, and we've sent probes to Mars, and we've seen things flying around, sent probes flying around in our solar system. So it is an assumption that outside of our solar system, the gravitational constant that's the same everywhere within our solar system is the same there too. So when we analyze things rotating around each other, we're assuming that the gravitational constant's the same, and then we use that to figure out how much mass they must have based on how they rotate and so forth, or revolve. Okay? So there are lots of things like that, lots of constants. Speed of light. We assume the speed of light is the same everywhere. Okay? And so if it was different somewhere in the universe, or there was some variation in that, it would be almost impossible for us to tell. All the evidence we have seems to indicate that all those things are the same everywhere. Like I said, we have no reason to believe there's no evidence that it's different anywhere. And so for the moment, that is our best assumption. About 90 years ago, a guy named Edwin Hubble, back in 1929, published a paper that described that he'd figured out that every galaxy in the universe is redshifted. What does that mean? That means that the light from it has been Doppler shifted and stretched out, okay, to lower frequencies, longer wavelengths, okay? Which, if you remember the Doppler effect video, told us that the object was moving away from us. Well, how can we tell that the light was redshifted? We don't know what color it was to begin with, right? It could have been any color. Well, we know the energy levels of hydrogen, right? Like we saw in our last video on spectra. And we know where those emission lines should be from hydrogen, or absorption lines, if it's an absorption spectra. And if we don't see them at the right frequencies, if they're shifted to longer wavelengths or higher or lower frequencies, that means that light has been redshifted, meaning us and the galaxy are moving away from each other. Okay? Whatever frame of reference you want to take on that, we're getting farther apart. And that's what we see. In fact, the farther away the object we're looking at, the more redshifted it is. In other words, the faster we're moving apart. So things that are close together are moving apart slowly. Things that are farther away are moving apart more quickly. Okay? So these two factors, first, that everything is redshifted. Every other galaxy is redshifted, moving away from us. Okay? I should say every galaxy outside of our local group. We'll talk about local groups in the next video. Okay? It's 20 to 50 galaxies near us. And there are billions of other galaxies, as we'll get to in the galaxies video coming up next. All of those billions of galaxies, anyone we've looked at it and analyzed the light from, they're all redshifted. Okay? Pretty much confirming those that Hubble had looked at, which was a significant enough number to publish a paper and to have it well known and later get a telescope named after you. So he figured out that there was an exact relationship between how far away an object was, a galaxy, a star, a quasar, and how fast it was moving apart from us. Okay? So you could actually, once you had this constant, you could measure the redshift of a galaxy, and by that you could calculate how far away it was. Okay, it was that constant of a thing. So he began to think, well, if everything's moving away from us, that means yesterday it was all closer together. Okay? And if yesterday was closer together and the day before that it was closer together, eventually we have everything at a point. And this was the development of the Big Bang Theory. Okay? That if it's moving away now, it must have been closer yesterday, it must have been closer last year, must have been closer 1,000,000 years ago, must have been closer 1,000,000,000 years ago. And if we extrapolate back, everything must have been together 13.7 billion years ago. So if everything in the universe was at a place 13.7 billion years ago and has spread out from there, that became the idea of the Big Bang. Which, by the way, was not the original name of the theory. It was actually a name that was created by its opponents to make fun of it. Yeah, what's this, like the Big Bang Theory? Yeah, sure. And it was such a cool name, it stuck, and now that's what we call it. So at this point we've got, decent logic, right? Everything's going away now. It used to be closer together. Well, perhaps there was a beginning. Okay? This is coming at a time where people thought the universe had been here forever. It had always been here, called the steady state theory. It used to be taught, even when I was in school, which wasn't 1929, we were taught about the possibility of the steady state theory. Okay? Which by now pretty much no one believes is a realistic possibility. No scientists, no cosmologists would probably be even a better way to say it. Okay? Because it doesn't match the data that we get from looking at the universe. Okay? So the universe must have been created at some point in time. And it appears as though that time was 13.7 billion years ago, when we extrapolate back the speed that things are going and how far away things are and all that. What was predicted? Well, at that point, we predicted that the universe all began at a point. Before that, there was no matter, no energy, no space, and no time. Whoa, no space. What do you mean? Wasn't the Big Bang like planets being flung out into space? No, actually, the theory says nothing existed. None of our physical universe was here. Our entire physical universe was created at this point in this Big Bang. Okay? And so we see that at that point in time, and we don't know why it was created or what created it from a scientific standpoint. Okay? So at that point, we know what would happen just after that. We'll talk about how we can see that and extrapolate some of that. But before that, we don't know. But at that point, everything, time, space itself, was created. Okay? So, once again, it's not that space was there and these things were flung into space, but space itself began to expand and began to take shape. As you might remember from gases, if you put them under pressure, you increase their energy, their temperature, and as you let them expand, they cool down. So if the universe has been expanding and matter has been getting farther apart, that means it's been cooling down. So when it first happened, it would have been incredibly hot when the universe first was created. And so in that incredibly hot situation, once we got to the point where there were electrons and protons, well, then light could travel around, but it would be continually absorbed by these electrons. Okay, and so that light would just keep bouncing around from one electron to the next, going a different direction all the time. It only happened about what we now believe is about 400,000 years after the Big Bang that finally the universe cooled down enough that the electron and the proton could combine to form hydrogen. And once that happened, then the light could travel straight. Okay, well, what does this mean? This means that the entire universe was glowing with this light at 400,000 years ago, and then all of a sudden that light could travel straight and not get absorbed. Well, as the universe expanded, that light has still been traveling. In 1948, we predicted that this light is still traveling. So we can look back to see 400,000 years after the Big Bang, which is about 13.7 billion years ago. We should be able to see that light still traveling to us. Okay? We should be able to look back in time 13.7 billion years. At that point, the universe was absorbing and resending light, and so we can't say anything from before that because it was opaque, you might say. It was like looking at a piece of wood. You can't see through it. The whole universe was opaque because the light was continually being reabsorbed and reemitted. At this point, they predicted we could see this. Then 17 years later, in 1965, Dickey, Pebbles, Roll, and Wilkinson at Princeton were starting to develop some tests to try, or methods to try and measure this cosmic microwave background radiation. A couple guys down the road making a radio tower. Their names were Penzias and Wilson. Okay, Penzias and Wilson found this background radiation that was really bugging them, getting in the way of everything. And sure enough, when Dickey, Pebbles, Roll, and Wilkinson looked at it, they realized what it was and its cosmological implications, that we had found this background radiation. And as we began to continue to look at it, any point in the sky, any direction, from anywhere on Earth, you can see this coming in from everywhere where it's not blocked. Obviously, if you're looking at a star, you're going to see the star, not what's behind it. But everywhere there's not a star in a way, anywhere in the night sky, there's this cosmic microwave background radiation coming to Earth. And it's pretty much the same everywhere. Okay? So you can imagine this would be pretty difficult to explain in another way. What could be producing this exact same radiation everywhere? Okay, well, we already had an explanation, and it already predicted it, which, by the way, is one of our qualifications for becoming a theory, is to be able to have a hypothesis that can predict the outcome of an experiment. We predicted that we would be able to find this cosmic background radiation, and we found it. Okay, so voila, into theory status. But that's not all. Things that are hot glow. Okay, that's just like the universe we're talking about. But if we have a fire, it's hot, it glows. Our bodies are hot, they glow in the infrared. Okay, right? Military gets on infrared goggles and they can see your body. Okay, if you remember the old Commando movies, right, or Rambo, maybe it's, I don't know, or Predator, I don't know, one of those, they cover their bodies in mud to try and cover up their infrared radiation. Okay, so everything glows. The mud radiates just at the same temperature as all the mud around it. Okay, so it makes it hard to pick you out from the mud. So everything glows, and it's called Blackbody Radiation. And it has a curve that looks something like this. Okay, and that curve just shifts frequency of light depending on what object is emitting it. Well, as we study this microwave background radiation, it fits this curve pretty much exactly. Okay, they're tiny error bars, but as you can see, here it is. You can see it's the same as a black body radiation curve, meaning it was created by something that was hot and glowing, which turns out to be the universe 400,000 years after the Big Bang. So a second piece of things that was predicted and then found to be true. It was predicted it would be blackbody radiation, and it was found that it was blackbody radiation. The last thing was, going into the 80s, we realized that the universe isn't uniform in the sense that it's the same everywhere, like a bowl of pudding. But there's lumps called planets, and lumps called star systems or solar systems, and lumps called galaxies, and lumps called galactic clusters. It's not spread out evenly. Because of that, it means that the universe 400,000 years after the Big Bang couldn't have been spread out evenly. If it was, gravity wouldn't have pulled it together into galaxies and planets and so forth. So when we look back, we should see fluctuations in the background radiation. Well, guess what? We couldn't find them. And we got to being able to measure it more and more accurately and couldn't find it. And I was in college about this time, and I remember my professor going, we are very close to having to scrap the Big Bang Theory because there aren't fluctuations. We can't find them. We're getting sensitive enough that we should be measuring these. And if we can't measure them, it means that our predicted explanation for this background radiation would not have created the universe that we see today. And therefore it doesn't match up with the evidence, and we'll have to figure out something new. Well, by the end of that course, we discovered it. It was 1992, and we discovered the fluctuations in the background radiation, where it's a little more dense, and therefore that would have collapsed into a galactic cluster, and parts within that into galaxies, and within that into stars, and so forth. So, last thing about this background radiation, it is, if something next to you was emitting that, it would have to be at a temperature of 2.725 kelvins. So when we talk about the background radiation, we talk about it at 2.725 kelvins, meaning it's the temperature of something that cold releasing it. By the way, that's a little less than 3 degrees above absolute zero, where the molecules stop. Okay? Why is it so low? Because it was so far away, and even though it was really hot, it's been expanding since there, and so that stretched out the wavelength, made it a longer wavelength because of the Doppler effect, and so it looks like it's that cold because it's been stretched out because it's coming from so far away. That's the Big Bang Theory. Those are the lots of the major evidence that's been found to lead us to call it a theory. The things we predicted and then found, which are keys to having a theory. So enjoy it. Go out, look up. If you can see in the microwave range, look up and enjoy the bright night sky filled with microwave radiation. We'll see you next time on the Scientific Adventures of Beardman to look at galaxies.